So from this class onward, we are going to discuss about antennas. So once we complete the antennas, we will go back to transmission lines again. Now, as you know, any wireless communication system, in the wireless communication system, the basis is radiation of electromagnetic wave. So there will be 2 points. One point is the transmitting point, other point is the receiving point. They are not connected by a wire. They are in free space. From one point, from the transmission point, electromagnetic waves propagate in free space and they are received by the receiver at the receiving point. Now, at both these points, the transmitting point and the receiving point, the device that is used is called antenna, and the phenomenon that is used is called electromagnetic radiation. By definition, we say radiation to be a disturbance of electromagnetic field. So if there is electromagnetic field and there is a disturbance, which means there is a time varying electromagnetic field. So with time the electromagnetic field changes. So it is disturbed. So if there is a disturbance of electromagnetic field, the disturbance is called to be radiation. If there is no disturbance in electromagnetic field, which means electromagnetic field does not move, it remains static, then it is a static electromagnetic field. It is not related to radiation. So the radiation is a disturbance of electromagnetic field. And this disturbance, once this disturbance is created, it will propagate away from the source of the disturbance. Wherever we create the disturbance, by nature of radiation, the electromagnetic field will propagate away from the source or from the point where the disturbance is created. Then the total power in the electromagnetic field or electromagnetic wave, it will not decay with distance. As you move away from the source point. Source point means the point where the disturbance was created. From that point, as you keep on moving away, the power contained in the electromagnetic wave will not be decayed. The power will remain constant. Power will remain same as you move away from the point of disturbance. It does not mean that the power will remain same along a particular direction. If you take any direction along that direction, the power will not remain same. But over the whole space, the power will remain same. Not along a direction, but over the whole space. Why so? Because power gets distributed over the space. Therefore, the power will be same over the whole space, not along a particular direction. Now, what is the cause or the source of this disturbance? The cause or source of the disturbance is a time varying current source. So if you have a time varying current source, if we have a time varying current source, then that will result in creating a disturbance, and a time varying current source is always associated with an accelerated charge. Because it is associated with accelerated charge, the accelerated charge, or if there is a charge which is accelerating, that creates disturbance or that creates radiation. So accelerated charge is a source of radiation. So from that we get radiation. That we will discuss when you take a complete course on antenna. But for this course, just remember that accelerated charge is the source of radiation. Now let us consider steady state charge oscillation. And what happens if we have a steady state charge oscillation? Look at two charges here, a positive charge and a negative charge, which are separated by an infinitesimal distance dl. Infinitesimal distance, what by what we mean when we say infinitesimal distance is dl is much smaller compared to lambda. Lambda is the wavelength, so dl is much smaller compared to lambda. So under that condition, what is happening? Let us see. So the charges are stationary. Initial condition is the charges are stationary. Stationary means they are not moving. Their position is fixed. So from that point we start. The two charges are oscillating. From that point we will go to the next stage, which is the two charges are oscillating in amplitude. It is sinusoidally. So what is meant by amplitude in sinusoidally means they are oscillating so that the amplitude of the oscillation is varying sinusoidally. Then they are associated with a phase. Since and there is a sign, sinusoidal means there is a sine function. So sine function can also always have additional phase. So the two charges are oscillating. Their oscillation is sinusoidal in amplitude and the oscillation is in phase. This is the condition for the two stationary charges. And then consider a dipole. If we consider a dipole, in the dipole we have two charges, two opposite charges. Now these two opposite charges, when they are oscillating, the charge keeps on moving. When the charge moves, a moving charge results in a current. Therefore, the dipole provides a current path. It will provide us a current path, or there is a current. If we have a dipole which consists of two charges, two stationary charges, which are oscillating, then the dipole provides us a current path. Since there is a current path, it allows the charge distribution to alternate back and forth. What does that mean? That means the positive charge is moving towards the negative charge because it is attracted by the negative charge. So positive charge will move towards the negative charge. Similarly, the negative charge will move towards the positive charge. Similarly, the negative charge will move towards the positive charge. So after a time, the positive charge will reach a point where the negative charge is. The negative charge will reach a point where the positive charge is. Because of the attraction, they will keep moving. They will cross each other at the midpoint region of, and they will keep on moving. Reason is when they cross at the point, at the midpoint, they have acquired sufficient momentum. Because they have momentum, they will keep on moving till the momentum goes to zero. So the negative charge will come to rest at the position where the positive charge is. Positive charge will come to rest at the position where the negative charge is. Then again they will be attracted to each other. Then they will be moving towards each other. So there will be oscillation. So positive charge will go to negative charge, come back to its position, again go to negative charge, come back to its position. Same thing will happen with the negative charge. So this is the whole thing is equivalent to this whole phenomenon, this positive charge going to negative charge coming to positive charge, or their motion, the motion of the charges back and forth motion is equivalent to an oscillating uniform current, which is called an ideal dipole, an electric dipole. Not a static dipole, this is an ideal electric dipole in the sense of antenna. The oscillation of charges back and forth occurs between the two ends where the charges are initially located. So this is equivalent to this. Now let us see what happens in this case. So this is similar to a wire dipole antenna because a wire carries current. Here we have seen charge is moving. Moving charge is equivalent to current. Therefore, this is equivalent to a wire dipole antenna. So look at the right hand figure where we have a wire The top is shown by plus sign, bottom is shown by the negative sign. The OR is towards upward and it extends towards upward and downward from its center. Downward it ends as the negative sign, negative charge, equivalent to negative charge. Upward it ends in the positive sign, equivalent to positive charge. So we have a OR dipole antenna. The OR dipole antenna is excited with a sinusoidal current because oscillation is occurring. Oscillation is a periodic phenomena. Periodic phenomena can be described by a sinusoidal function. Therefore, there is a sinusoidal current excitation of the OR charges. The frequency of the wave or the frequency of the sine wave is f. Now, if f is the frequency, then the time period t is equal to 1 upon f. So, frequency is f and t is equal to 1 upon f. Now, I assume that this current source, the current on the OR, is switched on when small t or little t is equal to capital T by 4, which means at the time instance when it is minus 1/4 of the time period. So small t is equal to minus capital T by 4. We started this. We excited this at small t is equal to minus capital by T by 4. Now on the upward current, that will create excess charge on the upper half and deficit of charge on the lower half. Once you excite it, then the current will be from negative to positive. So the upward current will create excess charge on the upper half and deficit of charge on the lower half. What does that mean? That means the positive charge is moving downward and the negative charge is moving upward. Negative charge is accumulating on the upward, therefore excess charges on the upper half and lower half will be deficit of negative charges. So deficit of charges on the lower half. It starts moving in this manner. Now look at this figure, the right hand figure. The charges are at top and bottom. Therefore, the electric lines of force will start from the positive charge and it will end on the negative charge. So, electric lines of forces are shown here. They are starting from the positive charge, then they are moving and ending on the negative charge. So, this will be the distribution of the electric lines of forces from positive charge to negative charge when the oscillation has just started or when small t is equal to minus capital T by 4. Then we come to a point where the peak charge build up. Now when the peak charge will build up, we started with small t is equal to minus capital T by 4. Peak will occur, as you remember, if you remember a sine wave, in the sine wave, 0 occurs at t is equal to 0, then maxima or the sine becomes pi, sine pi by 2, that occurs at t is equal to capital T by 4. So here we have started 0 at minus t by 4, therefore the peak will occur or the maxima will occur after a time of t by 4 minus t by 4 plus and t by 4 gives you 0. Therefore, the peak of charge will build up when small t is equal to 0. So, small t is equal to minus t by 4. We started. Now, small t is equal to 0. We have reached the peak of the charges. Now, when the peak of the charge will occur, then the peak of charge will produce a voltage between the two halves, upper half and lower half. There will be a voltage between the upper half and lower half. The top positive charges, when this occurs, then the top positive charges, they will be attracted towards the bottom negative charges. They will create a current and maximum at t is equal to t by 4. Now this is at t is equal to 0, the charge buildup. Now consider the condition when small t is equal to capital T by 4. When small t is equal to capital T by 4, we started from small t is equal to minus t by 4. We reached the maximum or peak point when t is equal to 0. Then when small t is equal to capital T by 4, again we will come back to 0. Then we will go to negative peak. So when you come to 0, the charges are getting neutralized. When we started, the charges were not neutralized, but there was no current. Current was 0. Now the current becomes, charges gets neutralized as it comes back to the second 0. So sin omega t or sin ft, if you plot it, so from 0 you go to maxima, then come to 0, then you go to negative maxima, then you come to 0. So now we have come to, from 0 we went to maxima, now we have come to 0. So 0 means the charges get neutralized. Both the charges are at the center point. So both the charges are at the center point, therefore they neutralize each other. The positive charge and negative charge, they neutralize each other. Since they neutralize each other, there will be no charges for electric field lines termination because they have joined together. So there will be no point from which it will start, where from and on which it will end. So there is no point of neutralization, there is no point of termination. So it is a loop, it becomes a loop. So starting point and ending point are same, which means it becomes a loop. So they form closed loops near the dipole. So we started with clear loops, unclosed loops, open loops. Then at t is equal to 0, we started with open loops. Then at t is equal to t by 4, we have reached a point where they are closed loops. Once they are closed loops, they are detached from the dipole because there is no starting point, there is no ending point. So they get detached from the dipole. So electric lines of force get detached from the dipole. Once they get detached from the dipole, they will move away from the dipole in the space surrounding the dipole. In the next cycle, next quarter cycle, what will happen? Negative charges will accommodate or accumulate at the top, and positive charges will accumulate at the bottom of the dipole. That will happen in the negative in the next cycle. So look at the bottom figure. In the bottom figure, you can see and the negative charges are at the top and positive charges are at the bottom. So the electric lines of forces, if you look at the electric lines of forces, their direction have changed. If it was in the beginning, if it was in the clockwise direction, now they will be in the counterclockwise direction because they will move from the bottom to top. Earlier they were moving from top to bottom. In the top there was positive charges. From always it will come from positive to negative. So in the beginning it was in the clockwise direction. In this cycle, in the next quarter cycle, it is from the counterclockwise direction. Now, now consider what happens near the dipole. Near the dipole, the fields are most intense because they are near the dipole. So the as you know, the electric field expression, suppose the charges are not moving, then the electric field expression E is equal to 1 by 4 pi epsilon r q by r square. So when r is small, the field intensity is maximum. So when you are near the dipole, it will be maximum. So near the dipole, the fields are most intense and they are always normal to the oscillating charges on the dipole. That you know from the definition of field, or when you have read electrostatic, there you will already have seen that the fields will be always normal to the normal to the charges. Therefore, here they will be normal to the oscillating charges on the dipole. Now, with time, what happens is the electric lines of forces, they detach from the dipole when they are neutralized, when the dipoles are neutralized or when they cross the center point. So at that point, they get detached from the dipole. They form closed loops in space at the time of detachment, and they spread outward from the dipole. So they keep on moving from the dipole. Now, if you view this in terms of current, the conduction current on the antenna converts to displacement current in space. That is the phenomena what is occurring. You start with conduction current, and the conduction current is transformed to displacement current. That is, in physics or physically, this is what is happening. So the antenna converts conduction current to a displacement current. So the conduction current on the antenna gets converted to displacement current, which consists of longitudinal fields near the antenna, solenoidal fields away from the antenna. And the solenoidal fields are created by the wire loop. These are satisfied, or they satisfy the continuity condition. Next. Now, this process continues. Since the process continues, process of oscillation continues, therefore this process continues. If this continues, this is producing radiation via the electric field components, which are transversed to the radial direction, as we have just seen. These are perpendicular to the direction of the to the line, which is perpendicular to the line, which is connecting the positive charge to the negative charge. Therefore, they are transversed to the radial direction. They propagate to large distances from the antenna. In fact, they propagate up to infinity. They do not stop. They keep on propagating. They do not stop. As we discussed earlier, the radiation does not decay. So there is no power loss. So they propagate to infinity. This confirms the general radiation principle. The principle is there should be accelerating charge for production of radiation. Now, since there is oscillation, due to oscillation, the charge is accelerating. So it is always changing its direction. Change in direction is equivalent to acceleration. And this confirms the general radiation principle. The oscillating charges, they create regular disturbance. Because of disturbance, the radiation is continued. Radiation is created, and regular disturbance will result in continuous radiation. The frequency of charge oscillation determines the frequency of the radiated wave. So the frequency of charge oscillation is equal to the frequency of the radiated wave. When you design antennas, the antenna design is such that it will support the charge oscillation. If it supports the charge oscillation, then only there will be radiation and antenna will work properly. If charge oscillation is not supported by any structure that we have designed, that will not act as a proper antenna. So for proper antenna, and this should occur. Now let us see from another point. Let us consider a transmission line. So a two-wire parallel transmission line. You can see here we have portrayed a two-wire parallel transmission line. On the two-wire parallel transmission line, the current is shown by arrows. Then the electric field and magnetic field are shown by dashed arrows, solid arrows which are vertical, solid and dashed arrows, and the cross and dot. So they represent the magnetic field, and the arrows represent the electric field, whereas the cross and dot, they represent the magnetic field. So that is the field distribution on the two-wire antenna. If we have such a two-wire antenna at a far distance from the antenna, these fields will exist, but you can see the direction of these fields is changing. Within the two wires, the fields will be confined. So whatever field is existing between the two wires, they will be confined to within region. Outside the two wires, you can see the cross in the top. It becomes a dot in the bottom because the current has changed its direction. Similarly, dot in the top becomes a cross in the bottom, outside. If you look at the outside portion, not the inside. Inside portion, we do not worry because that holds the way, because there is a small distance between the two wires, so the electric field is held tight there. So that is not going away from the inside of the wires. Outside part, you can see in the outside of the wires, the outgoing magnetic field becomes incoming magnetic field on the bottom layer. Similarly, for the top, the incoming magnetic field for the top becomes outgoing magnetic field for the bottom. Similarly, the solid vertical arrow becomes solid downward arrow. Solid downward arrow becomes solid vertical arrow. And dashed arrows for similar thing. Which means at the if you go to a far distance from the antenna, from these wires, there the fields will be exactly in opposite direction. If they are exactly in opposite direction from the two wires, from one wire, suppose it is in the upward direction, from the other wire it will be in the downward direction. So they will cancel each other. Vectorially, when we add them, they will cancel each other. So there will be no resultant field in the far direction from this antenna, from this line. So if you take a two parallel transmission lines, they are not going to radiate. But just change this line slightly. At the end of the line, bend the line. So the upper wire, you bend it upward. Lower wire, let us bend it downward. Then you can see the current distribution. Current distribution in the bent portion is in the same direction. Since the current distribution is in the same direction, therefore the fields will be also in the same direction. So this region, this bent region, will result in a radiation or in an effective electric field and effective magnetic field. Because the current in both of these are same, they will add up. Since they will add up, they will not cancel. The parallel portions, the fields will be cancelling, but this portion, this vertical portion which is bent, their current distribution is same, in the same direction, therefore fields will be in the same direction. So the fields will add up, they will not cancel, which will result in a radiation, which will result in a net electric field, which means at the far field, in the far zone, we will get a field always. So here, let us conclude our discussion on the basic of antenna, then we will come to particular definitions of antenna. So let us take a break here for 5 minutes.